Hello APCal class. We are going to start the notes for section 3.1 and it does follow the textbook for that section. So what we're looking at now and what we're starting in this unit is extrema, and this will be, first of all, we're just going to talk about how to find extrema on a function using the derivative, and that's going to lead us into first and second derivative tests, and not necessarily in this unit but in this same chapter in the book we'll also get into some applications with that, which would involve some optimization type problems. Okay, so in here it says, in calculus, much effort is devoted to determining the behavior of a function for an interval I. We'll investigate such questions as, does it have a maximum value? Does it have a minimum value on that interval? When is it increasing? When is it decreasing? Those are all things that we can determine using derivatives. All right, so in these first diagrams here, it says a function does not have to have a maximum or a minimum on an interval. For instance, in figure 1, you can see that, okay, so we just have this parabola, x squared plus 1, has both a maximum and a minimum on a closed interval, -1 to +2. So that's what we have here. We have closed dots at the ends, -1 to +2. It's just this parabola function. And so clearly there's a minimum because that's where the vertex would be, and the maximum because it is a closed interval. We can see that the highest point here would be at where x equals 2, and it looks like the maximum value would be 5. Okay, so that leads us into the extreme value theorem. This is important. Any theorems that they list are important, and there's usually an acronym, EVT, for this one. So if they give it an acronym, that means, okay, we're going to talk about it a lot, so it is important. It says if f is a continuous function, or if it's continuous on a closed interval, so closed is very important there, so you have to have a closed interval, and the word continuous. So continuous and a closed interval. Okay, those two criteria, if those are met, then we know that f has both a maximum and a minimum. Okay, so that's really important, but you have to meet all this criteria. First, we have to know that it's continuous. We have to state that it's a closed interval. Then we can say, yes, there's both a maximum and a minimum on that interval. So let's go back and look and see. We saw that was the case here. We have a continuous, because parabolas are continuous. Any polynomial functions are continuous. So it's continuous, and we know that it's a closed interval. So we have both a minimum located at the vertex and a maximum located at whatever, in this case it's at an endpoint. Okay, so in figure 2, let's see where this definition kind of breaks down and the reason why we don't have a maximum in this case. So if we look, it's continuous because it's a parabola, however, not closed, right? Because we can see our endpoints are open circles. So therefore, we do have a minimum at the vertex, but what we don't have is a maximum because it's an open circle right there. Okay, so what that means is that, really we can get infinitely close to this, whatever that point is, and we really don't have a maximum value. Okay, so that's this part of the definition has to be closed. And then the last figure here, we see that it's closed, but they've kind of changed this function and made it into somewhat of a piecewise. It is a parabola mostly, except when x equals 0, they've redefined that point. And so therefore, we don't have a minimum because, this isn't the lowest point anymore, and it looks like this is at the same, so we'd get infinitely close to this lowest y coordinate, so we don't have a minimum. Okay, so that's why it's important for that criteria all to be met. It has to be continuous, and then also on a closed interval. Okay, so relative extrema and critical numbers. Okay, critical numbers are important. We're talking about this a lot. It says the graph, this cubic graph we have right here, has a relative maximum at the point 0, 0. Okay, so we can see that right there. And it also has a relative minimum at the point 2, -4, so down here. So when we think about relative extrema, those are just any hills or valleys or peaks or whatever you want to think, or valleys that occur along that function. Even if they're not the absolute lowest or the absolute highest, they're relative to the other points around them. They are a max or a min. Okay, so that's the way you should think of those. Okay, so this definition, relative extrema, isn't going to be quite as important as absolute, because the extreme value theorem, that's related to absolute extrema, not to relative extrema. But basically this is just kind of recapping what, it's the highest or lowest point relative to the others that are around it. Okay, critical numbers. Now this is important. Okay, it says let f be defined at c if the derivative, so f prime of c, is equal to 0, or if it's not differentiable at a certain point c, or x coordinate c, then c is a critical number of f. So a couple diagrams to illustrate what they're referring to here. This would probably be the most common. F prime of c equals 0, okay? And what, on most curves that are, well behaved, that don't have, kind of weird things, this is called a cusp, and that's not very common, but it can happen. But on most, especially like polynomial functions, wherever you have a horizontal tangent line, that means that's where the derivative is equal to 0, because remember, derivatives are slope finders, and we know at like relative mins and maxes like this is where we're going to have a horizontal tangent line, okay? So that's called a critical number, where the derivative is equal to 0, but also it can be a situation like this, where the derivative doesn't exist. The reason they say it doesn't exist here is because what we have is a situation where you can't really draw one single tangent line through here. This is called a cusp. And there are certain functions, typically what they are they're functions that have a rational exponent, like a fraction exponent. You get something that looks like this. We'll look at some of those. But this would be considered a critical number because a min or a max can exist here at a cusp, okay? All right, but that one's less common, but that's the situation where the f prime would be undefined, or the function's not differentiable, okay? Okay, so it says relative extrema occur only at critical numbers, so that's what we're getting at here. It says if f has a relative minimum or relative maximum at x equals c, then f is a critical number, okay? So on the graph, the critical number is either going to be, something that looks like this, where you have f prime is equal to 0, horizontal tangent line, or possibly where you get like this cusp-looking thing where it doesn't exist, okay? So guidelines for finding absolute extrema on a closed interval, okay? So this is really important and is related to the extreme value theorem, okay? So when they say find the extreme value of this continuous function on this closed interval, these are the steps. First thing is find critical numbers. So basically what that means is find the derivative of the function, set it equal to 0, and solve, okay? Now, if your derivative contains, after you find the derivative, if it contains a function that's basically rational, that has x in a denominator, then you want to set that denominator equal to 0 as well to determine where the derivative is undefined. Doesn't happen that often, but that would be part of your finding critical numbers, because we'd want to know where f prime does not exist. And so if there's a chance where it's undefined, where there's a denominator with a variable in it, then we have to set that equal to 0 and solve there. Okay, now once you find those critical numbers, evaluate each of the critical numbers that's in that interval. Okay, so whatever you found there, you have to evaluate those, and then evaluate each endpoint, because remember, extrema can occur at endpoints on a closed interval, right? The least of these values is the absolute min, and the greatest is the absolute max, okay? And, they just kind of make a statement here. We refer to the mins and maxes, it's the y-coordinates, right? So just some of the language there. The absolute min that's the y-coordinate, occurs at, that's the x-coordinate, at the x-coordinate where it occurs. So just kind of going back to what we were looking at here, we see that, we have a closed interval, it's continuous, so in this case a maximum occurred at the endpoint, a minimum would have occurred, this would have been a critical value here at the, when we set the derivative equal to 0 and solved, we would have gotten this x-coordinate of 0 and then plugged that in and got a 1 for our minimum value, okay? All right, so putting this into practice, it says find the absolute extrema of this function on the closed interval -1 to 2. Okay, so it's a polynomial function. We know it's continuous. Okay, so there's, as far as knowing that it's continuous, you have to know some things about, continuous functions. Any polynomial function is a continuous function. The main things that would make them discontinuous would be if you had like a rational function that had x's in a denominator, where you might have vertical asymptotes, or if it's a piecewise function, then you always got to check to see if those are continuous. All right, so we got continuous, we got closed interval. All right, let's see what we get here. Steps, okay, find critical numbers. So we want to find f prime of x. So we're going to do our derivative, 12x to the third minus 12x squared, and we want to set it equal to 0. There's not going to be any places where it's undefined, because again, our derivative is still a polynomial, nothing undefined there. Okay, so let's factor out 12x squared. Leaves us with x minus 1, and so our critical numbers, if I set each factor equal to 0, I'd get x equals 0 and x equals 1. So setting each one there. So setting 12x squared equal to 0 is 0, and x minus 1 equal to 0 is 1. Okay, so those are my critical numbers, okay? These are critical, I'm just going to label this critical numbers, okay? It's an important term. So that's what we've got right there. Now, once we have those critical numbers, we want to test. We want to test those, and they are, they're in our interval. 0 and 1, that's in our closed interval. So we want to test those, and we want to test the endpoints of our interval. Okay, so test, I'm just going to make a note here. I won't do this on all of them, but when you do this, this is, when you're testing for extrema, absolute extrema, this is what you always do. So you test your critical numbers, so I want to plug in f of 0, because that's one of my critical numbers. I want to test f of 1, and this is the work you would show on your AP exam too. You want to show what you're doing here. I'm testing my critical numbers now. I want to test. Now, you don't necessarily have to label that, but you do want to show this. You want to say, okay, they knew that they're testing critical numbers now. Do they test the endpoints as well? Okay, so you want to show that work. So I'm just going to label it here just for the sake of teaching this, but you don't have to do that on your exam. But I'm going to say critical numbers and endpoints, but we want to make sure we show that we are plugging those in, f of -1 and f of 2. Okay. Now, in questions like this, typically you're going to be able to use, you don't have to do all this by hand. You're going to plug, probably this into your calculator, and then you're going to start putting some values in. Now, for time's sake in the video, I'm not going to pull up a calculator and show you. You could easily enter these values in. 0 is real easy. We know that gives us 0. If we plug in a 1, we're going to get -1. If we plug in a -1, check that, you get 7. And if you plug in a 2, you get 16. Okay, so now what we're looking for of those 4 outputs, because we had 2 critical numbers, we have obviously 2 endpoints, which you're always going to have, and then you're looking for the largest and the smallest. So what we see is that absolute max is going to be, I'm just going to go 16. That's our biggest of these 4 numbers, and it occurs at x equals 2. Where does it occur? At x equals 2. It's important to say where that happens. Okay, and then we have an absolute min, and the smallest of those 4 numbers is -1. So that's -1, and that occurs at x equals 1. Okay, so that's it. That's how you state absolute extrema. Okay, so let's look at some other types of functions here. All right, so here's kind of the giveaway that when you see something like this, x to the 2/3 power, that's that kind of function that generates a graph that looks something like this. So get used to, we'll see it when we do the derivative, but when you see something like that, they're trying to give an example of a derivative that's, a critical number where you get the derivative as undefined somewhere. Okay, so as we do this one, let's do our f prime. So we always do our derivative to set that equal to 0 and find critical numbers. So derivative of 2x is 2. The derivative of 3x to the 2/3, so that's going to be minus, and that will now be 2x, and I take 1 away from 2/3, which would be -1/3 like this. Okay, and I'm going to set this equal to 0 now, right? So now think about this. So I have x to the -1/3, which is really like 2 over x to the +1/3, right? The reason I'm setting it up like that is because I want you to understand. All right, now look at this. We've got something where I could put something in for x and make this undefined, and hopefully you can see that that's going to be 0. So again, I just want to point out again, why are we worried about that? Because when we look at the definition of what critical numbers are, sorry, oh, right here. Okay, so where f prime of c is equal to 0, or f is not differentiable at c. Now, again, what that means, not differentiable at c, is it means f prime of c is undefined. And so what we're looking for are any c values, or any x coordinates where the derivative is undefined, okay? And that's what we're coming across on this example. Okay, so if I were to solve this, I would subtract the 2. I'd have negative 2, and then I'd have negative 2 over x to the 1/3 on this side. Okay, now if I were to, let's say, multiply that x to the 1/3 over to this side, right? Negative, oops. So if I were to multiply by x to the 1/3, I'd have negative 2x to the 1/3 equals negative 2, and divide that out. X to the 1/3 equals 1, and the cube root of 1 is 1, right? That's how I'd solve that. Or actually, I would take it to the 3rd power to solve this equation. I'd go, okay, I gotta solve for x, so I would cube that side, and I would cube that side. Okay, so I would get x equals 1. That's one of my critical numbers, because that would satisfy this equation. You can probably see that if I put a 1 in for x, it'd be 2 minus 2 over 1, so that works. Now the other critical number is going to be whatever, once you take the derivative, if you get this situation where you get x in a denominator, a denominator equal to 0 makes something undefined. And so if I set x to the 1/3 equal to 0, that would be, taking to the 3rd power again, I get x equals 0. So my critical numbers are now going to be x equals 1 and x equals 0. Okay, those are my critical numbers. So, because this is where it's undefined, right? So I'm just going to say x prime of x is undefined. I'll just write that note there, and that's why we have to list that one as well. Okay. All right, so now what we want to do to find our, we're going to test our critical numbers. Okay, so in my critical numbers, I've got 1 and 0, so I'm going to do f of 1, I'm going to do f of 0, and then I'm going to test my, my endpoints. Okay, so I'm going to test those, so we want to do f of negative 1 and f of 3. Okay, so we'll plug all of those into our function, and we'll see if we plug in f of 1, we get negative 1 for that. If we do f of 0, we get 0. If we do f of negative 1, we actually get negative 5 for that. And then f of 3 comes out to like a decimal number. It's negative 0.24. And that one you just have to, type that into your calculator to determine that. Okay. And so as we look at this, we can see that we've got an absolute max is actually 0. Everything else is negative. And our absolute min would be negative 5. So our absolute max is 0 at x equals 0. And then absolute min is negative 5. And that occurs at x equals negative 1. Okay, so we can see that one right here. All right, so hopefully you're understanding the process here. Find your critical numbers, test those back in the original function. So once you get your critical numbers, you're plugging those into the original function to actually find the point that's on that curve. And then you want to test the endpoints as well. Compare all of those numbers to find your largest and your smallest y-coordinates, and those will be your absolute values, or your absolute extrema. Okay? All right. In this example, so now we have a trig equation, so there's a little more math to do on this one that's maybe not as familiar, but we've solved trig equations before. All right, so we want to do our derivative first, so f, I guess we'll go with black, f prime, so 2 sine of x, that's going to be 2 cosine of x. And then derivative of cosine 2x, so this one's going to involve a chain rule, right? So remember, derivative of cosine is negative sine, and so that's going to change that minus to a plus. So I have plus sine 2x, but then I have to multiply by a 2 again, right? Because I have to do times the derivative of the 2x, and usually that gets put right in front, so I'm going to rewrite this. 2 cosine x plus 2 sine 2x. Okay, Now, we have to solve this equation when we set it equal to 0. So we're going to set this equal to 0 because that's how we find our critical numbers. Now, I don't see anything where it's going to be undefined because we don't have any fractions where we have an x in a denominator. And sine and cosine are continuous functions, so they're not undefined anywhere. Okay, so if I set this equal to 0, oops, keep bumping. Okay, so we'll have 2 cosine x. Now, maybe as I'm looking at this, I set it equal to 0. I don't really see anything I can do with the way it is. So if you recall, there's this sine 2x. There is there's a formula or a property. It's called the double angle formula, if you recall those from trig. And what that stated was sine of 2 theta, or sine of 2x, is equal to 2 sine x cosine x. And we're going to need that for solving in this case. So we've got 2 cosine x plus 2, and then it'll be 2 sine x cosine x. So 2 times 2 sine x cosine x, which will be a 4 in front then. Okay, so if I were to, so I got 2 cosine x, 4 sine x cosine x. If I look at this expression and I need to solve it, usually you're looking to factor something. So now I have a common factor of cosine x and a 2 in common. So I'm going to pull that out. So I got 2 cosine x, and then I'm left with a 1. Remember, if you factor out the entire term, you got to put a 1 there. Plus, and now this is going to be 2 sine x. And now I can set each factor equal to 0. So 2 cosine x equals 0. And I can also set 1 plus 2 sine x equal to 0. And so divide the 2, cosine x equals 0. And over here, if I subtract 1 and divide by 2, I have sine x equals negative 1/2. Now, here it said we're going to find in the interval from 0 to 2 pi, which is good because that's typically where we work with trig functions. And if you recall, cosine is going to be 0 wherever x coordinates are 0 around the unit circle. And those angles would be 90 degrees or pi over 2, and then also 270 or 3 pi over 2. And for sine being negative 1/2, well, sine is negative in quadrants 3 and 4. And remember, the reference angle for a sine equal to 1/2 would be like a 30-degree angle or a pi over 6. So if I go pi over 6 into quadrant 3, I'd be 6 pi over 6 at at pi or at 180. If I add one more pi over 6 to that, that would be 7 pi over 6. So I'd have 7 pi over 6 would be a quadrant 3 angle. And then in my quadrant 4 angle, if I it'd be 12 pi over 6 would be a 2 pi. So if I go back one space from that, that would be 11 pi over 6. So those would be my 4 critical numbers that I would want to test. And then I also need to test endpoints on this. So I'm just going to list these. So I've got f of pi over 2. I've got f of 3 pi over 2. I'm going to have f of 7 pi over 6, f of 11 pi over 6, and then I have to test my endpoints, f of 0, and I'm not labeling them like I did before. I'm just going to write them all down, and that's really all you need to do, but before I was trying to demonstrate what those were. Okay, so we need to test all 6 of these, okay? And for time's sake, I calculated these beforehand, but you'd have to go through and check these. But if I plug in my pi over 2 into this original equation, sine of pi over 2 is 1, and then cosine, and now this would become pi, so cosine of pi is going to be negative 1, so it's going to be like 2 minus negative 1. That actually turns out to be 3. Okay. And I'm not going to talk you through all of these, but if I plug in 3 pi over 2, I'm going to get negative 1. If I plug in 7 pi over 6, and this is a rounded value since we're finding mins and maxes, this is negative 1.5. And if I plug in 11 pi over 6, I get also the same thing, negative 1.5. If I plug in a 0, I get negative 1. And if I plug in 2 pi, I also get negative 1. Alright, so it looks like my max, absolute max, is going to be 3, which occurs at pi over 2, x equals pi over 2, and my absolute min is going to be, it looks like negative 1.5, which does occur in 2 different spots, but there is just the one min, so it's negative 1.5, and that occurs at, we see 7 pi over 6 and 11 pi over 6. Okay, so that is what we do to find our absolute mins and maxes, or our extrema. Okay, now I didn't verify these on the calculator, but that is something that we can definitely play with and take a look at. Okay, so I'm going to stop here with the video, and we'll finish up the last examples on the next.